So welcome all of you from Krakow and from abroad. So now I will only mention that the one change was done. Grzegorz Reichel-Mieldziejcz is now Dr. Reichel-Mieldziejcz and is now joining us from Spain, from Catalonia, more precisely. From Barcelona or from Castelldefels?
From Castelldefels. I'm in the office
close
now.
to Barcelona, at the beach. Good. And now, okay, it's time to introduce our speaker. So Anna Szczepanek is Doctor of Mathematics, works in the building close to us, together with Wojciech Słomczyński, will tell us about ergodicity of Kusuoka measures of quantum trajectories, and I hope we'll learn more about Kusuoka measures and ergodicity as well. So Anna, please, you have a privilege to start the first talk this year. Go ahead. You are muted now.
Yes,
Anna.
yes. Everything should work now, right?
Yes, now we can hear you. Yes.
Okay, very good. So yeah, as you can see from the title, there's like 3 ingredients in this talk. It's first of all, it's all those strange Kusuoka measures. Then it's quantum trajectories, and then there's also ergodicity. So there's gonna be these three main topics. I will start with some general theory of Kusuoka measures, but very briefly. Then we will like switch to quantum scenario, which is gonna produce Kusuoka measures. We will see how quantum scenarios can produce Kusuoka measures and why it matters. And then we will discuss ergodicity, but don't worry, I will try to be as intuitive as possible, and also we will rather focus on some geometric features, not on some crazy theory. So lots of intuition and imagination, not much proofs or hard theory. Okay. First of all, a short refresher on shift spaces, and also this is like kind of preliminary slide to settle notation. So we will work on the space of sequences over some finite alphabets. I can already tell you that those final alphabet will be linked to results of quantum measurements. So we'll have infinite sequences of measurement outcomes. The dynamics which happens here is described by the shift operator. So we're switching our sequences to the left. So the far left symbol disappears. And what's important, we will heavily rely on Kolmogorov theorem. So we will be dealing with probability measures on this strange space of sequences, but in fact, due to Kolmogorov theorem, what we only need is to define our measures on cylinder sets, right? So a cylinder set is a set of sequences where some first few symbols are fixed, right? So the cylinder I1 up to IN is all sequences which have those symbols I1, IN on the first n positions. And as I said, thanks to this theorem, there's some assumptions, of course, that go along with this theorem, but we will not be really, we will not care about them that much. What we want is to define the probabilities of cylinder sets in a reasonable way, and then if it's reasonable, it extends to the probability measure on the whole space of sequences. And as an example, something which is very familiar to everyone, I think, is the Markov measure. So the probability of some string of symbols I1, IN is defined as the probability of the initial symbol. And then we've got a stochastic matrix, which describes the transition probabilities between each pair of symbols, right? So the probability of generating I1 in the first step is hin, and there's we've got the probability of generating I2 given that we had I1 in the first step, and so on and so forth. And so this is Markovian, so the probability of generating the next symbol depends only on what symbol was observed in the previous step. Also, what I've got here is this assumption that the vector of initial probabilities is a left eigenvector of the stochastic matrix. This is important because we want all the measures we want to consider today are gonna be invariant under the shift operator. So this is here important because we want shift invariant measures. All the measures we consider today are shift invariant, and among the whole space of shift invariant measures, we're gonna look for the extremal points, so the ergodic measures. Okay, so what this has to do with quantum scenarios and what quantum scenario we want to consider. We want to consider repeatedly measured quantum system, finitely dimensional. Here we're gonna have k possible outcomes. So this is gonna be our alphabet of symbols 1 up to k. And importantly, we've got unitary evolution, which happens between each two measurements, right? So if the system is left alone, it evolves unitarily, and from time to time, well, the period, the space, the difference is in time when the measurements happens are the same. So the unitary evolution that happens between each two measurements is the same at each step, as we can see in this simple diagram.
I'm sorry, may I have a simple question? What kind of measurements you assume? Orthogonal measurements or generalized POVMs?
As for now, it's general POVMs.
And they are the same every time?
Yes, yes, the same.
Perform the same measurements?
The same measurement, yes.
Okay, I see. Thank you.
So what this procedure gives us is a Markov chain, but a Markov chain which happens on the set of quantum states, right? So this is what is called quantum trajectory. So quantum trajectory is what happens in here, this evolution from row 0 to row I, row 2, row 3. This is quantum trajectory. But this is in fact hidden from us. We don't have direct access to this trajectory. What we can observe are the outcomes, I1, I2, I3, and so on. And even though the evolution on the quantum states is Markovian, in here what happens with the probability of performing the next step only depends on when we were in the previous step when it comes to the quantum states, but with sequences of outcomes, the evolution is in principle non-Markovian. Most often it is not Markovian. It's a very particular situation to which maybe I will have a chance to get, but no promises as yet. But in general, it's not Markovian. So we want to keep in mind that the strings of outcomes in a non-Markovian way. So we have to somehow take this into account. So in fact, the Markov measure, which I showed you in the previous slide, won't work in here, right? That was the simplest example of a shift invariant measure, but it won't work in here. So we need something else. We need some measure on the space of sequences of outcomes that will somehow agree with the quantum scenario.
Sorry, Anna, one more question. If you have a string of outcomes, which is given, how would you know that it is in principle non-Markovian if you do not know where the string comes from?
If I've got one string of outcomes,
yes,
then I wouldn't know. If I've got like lots of them, then I would like do some analysis of probabilities and see if the probabilities agree. But in principle, I won't know.
Okay. So it's possible to say that the string is non-Markovian if you have, let's say, infinite amount of data.
In the ideal world, yes. In a non-ideal world, I would need lots of data.
Okay. Thank you.
But also what would help would be a very long string of outcomes, right? So we can basically we could, with a very long string of outcomes, we could check if the probability of transition between a given pair of symbols is more or less the same. I think, yes, an infinite, because there's also this problem of the initial state, right? Because initial state plays an important role in here. So ideally, we would need lots of trajectories, so lots of strings of outcomes evolving from the initial state, the same initial state each time, or in a less ideal world, even one string, but a very, very long string. But this is not a problem, because we are gonna deal with the non-Markovian. I mean, Markovian is implied in here. All I'm gonna say will work in the Markovian case, but it also works in the non-Markovian scenario.
Okay, thank you.
Okay, so let's go to the Kusuoka measures now. So we've got the set of linear maps, and we've got a family of K operators, and they've got to satisfy those two conditions, which may look familiar to you. And also, here's the initial state row, which is involved in this condition. So this right-hand side condition says, in fact, that the initial state row has to be invariant under this operation. And Kusuoka measure is defined as by the formula which you can see in here, which looks resembles various stuff from quantum mechanics, right? There's trays, there's matrices, there's daggers. It seems it may have something to do with quantum case. In fact, this Kusuoka measures did not arise in quantum stuff, but in stochastic processes on fractals. So this is kind of surprising that they also turn out useful in quantum mechanics. Now those two conditions which you can see in here, they resemble, I told you they may look familiar because they resemble the Krauss decomposition of a channel, right? It looks very much like Krauss operators. And in fact, what those two conditions do in here, they assure that the measure we obtain is well defined and is shift invariant. So those two conditions, which normally are required for Krauss operators, in here, they assure us that our measure is okay. So as long as we can come up with K operators which will satisfy those two conditions, so operators plus the initial state, right? So the initial state also plays an important role in here, because the operators in here, there's no state involved, but in here we need to find an initial state which will satisfy this condition. So the operators plus the initial state. If everything is all right, then the measure which we defined as the trace of such a product of matrices, it will be okay. It will be well defined and shift invariant. It will extend to the measure on the whole space of sequences of outcomes. It will be like an honest probability measure.
I'm sorry. So to have a better understanding of this concept, if you take small n number of measurements equal to 1, then basically depending on the law, you have a probability vector which has length k, number of cross operators, which tells us what is the probability of different outcome of a single measurement. Yes.
Exactly. Yes. Exactly.
And now, if n is equal to 2, you have like likelihood that at time 1 you got result I1, and then in the second measurement result I2. Yes.
Exactly. Yes. Yes. Exactly.
But by the way, but then this dynamics is basically under assumption that the measurement was done, but then you do not renormalize the state after each step, or one has to renormalize it.
Well, yes, of course. Like
So,
the normalization is inside. We will see later on. Because as for
okay,
now,
no,
in
but
fact,
the formula,
this is
so the formula here with trace. You don't need to rescale this trace by trace of.
Like rescaling would be conditional probabilities, right? On the assumption of what we got in the first measurement, we compute probabilities of the result in the second measurement, then we've got this renormalization. But in here, we multiply the probability of getting the first result times the probability of getting the second result. And this, like, you multiply the probability of the first by the conditional probability of the second, and the normalization actually cancels out. We will see that later on.
So the vector is normalized, basically. The vector, probability vector, it's always normalized.
Yes, this is a proper probability measure.
Okay, thank you.
Yes, here, and this is like, as I said, this goes back to stochastic processes on fractals, nothing quantum back in 1989. As you can see, Dirichlet forms on fractals. And actually in this a bit newer paper, it's because this original paper, I must say, is a bit technical because everything about this measure is involved in this language of fractals. But in the second paper, it's like there's a more general approach, and the Kusuoka measure itself is treated first as a measure on the shift space without taking into account all those fractals stuff. So I rather recommend going first for this newer paper only than consulting the original one.
Yes, I only recall there was such a notion like polycot resonances. I'm not sure whether this is the same person. So Wojtek, do you know this polycot, this author?
Yes, he's from Warwick.
And do you think this is the same?
I met him many years in Warwick many years ago.
So you think this is
I think
name of polycot
the same person.
The same person. Okay. There are not so many polycots in this branch of mathematics, perhaps. Okay. So thank you. So maybe let's ask the audience, are there any questions concerning the Kusuoka measures? Is it understandable? So Anna, I'm afraid we have to assume it is. Nobody objected. Are there any questions?
Yes, it is clear.
Perfect.
Okay. Please go. Please continue.
We will see all this process once again, because here it is like we mix in here like the quantum stuff and general stuff, but in fact all this is completely out of the quantum context as for now. We will now see how this Kusuoka measure will arise in the quantum context. So even if something was a bit too general up to now it will be a bit more specific over the next few slides. So I hope everything will be clear, even if it's not that clear yet for someone. Okay, so let's get back to our this picture and let's make it a bit more specific, okay? In here, because what we now have to do is to model all this repeatedly measured quantum system with some mathematical some mathematical notions, right? So what we do is we use an iterated function system. For each input state, we've got the probability of getting some outcome if we start from some input state row, and we've got the post-measurement state, which depends on the outcome we got. Okay, so in the first measurement, we observed the outcome as 1. It means that we followed this path with probability P1 of row, and we landed at the state F1 of row. And so now from this new state, we are in here in our quantum trajectory. From this new state, we can again, we've got like 3 paths to follow with probabilities. And so now let's say we follow this path with this probability, and we got the outcome 2, which means we landed in here. Okay, so this now answers the question about this probabilities and normalization a bit, because we see that in order to get a string of outcomes, we have to multiply those probabilities, right? So this probability times this probability, and so on. So the normalization will happen in here. Actually, inside this probability, there's gonna be normalization in order to get a proper quantum state. But this normalization will cancel out with this first probability, okay?
Yes, thank you. Mm-hmm.
And here we can get even more specific, because now we can have like proper formulas for those probabilities. This is like the Born formula. And the post-measurement state is given in the most, the post-measurement state is given in the most standard form it can be given. And so now we can see how this first probability will cancel out with the normalization of the post-measurement state. So the conditional probability, I agree, the conditional probability would be like trace divided by, maybe let's write it a bit more specific, I2 euro, not euro, but pi I1 euro, pi 1i. There's gonna be u dagger, and divided by the very first probability. This is the conditional probability of getting I2 if we got I1 in the first measurement. So here's this normalization, but if we multiply it by the probability of getting I1, it means that we multiply by this trace, which we can see in the denominator. So I1 u row u dagger. So what's inside, what's left is the trace of this product of matrices, and there's like the normalizations got cancelled out along the way.
Anya, there is a question in the chat. If the measurement is projective with one-dimensional projectors, do we obtain a Markovian measure?
Yes, we do. Maybe I will get back to that later on, but like this is like why I also kind of avoid this, because this is like then trivializes. Actually, I'm more interested in the examples of measurements when this is non-Markovian. But yes, this is true that for rank 1 POVMs, we get Markovian measures, exactly. Okay, perfect. So what we got is a candidate, is something that looks like a Kusuoka measure. Okay, this resembles the Kusuoka measure which we saw. Here I've got it a bit more friendly way. So here's the definition repeated. here's what we got from our quantum procedure. It looks familiar. We've got those operators AI1. They are a bit complicated, but I mean not complicated, but those square roots, and they are composed operators, but still, it looks very similar, this and this. So, but what we can't yet say we've got Kusuoka measure, because what we need to check those two conditions, right? To see if what we got is actually a probability measure, because as for now it's on some expression, we're not yet sure if it will extend to a measure on the whole space. But this is now actually very, very simple to verify. What we've got is U dagger pi I U. This is this first condition, so this is obviously U dagger pi I U dagger. We can sum this up in here, and of course we've got the identity inside. So this is the identity, right?
There is no dagger in the second.
Of course. Yes, thanks. So the first one is simple. How about the second condition? We need to come up with some candidate for the initial state, right? Which will satisfy pi I U this time, rho U dagger UI. How to come up with this candidate? Actually, I don't know. The only state which I can reasonably check is the maximally mixed state. So the identity normalized, of course. And if we do this, this of course will be like 1 over D times the sum of the projectors or the measurement operators, which is of course again the maximally mixed state. So fortunately, the maximally mixed state works in here. So yes, if we take the measure generated by our repeatedly measured quantum system, which started from the maximally mixed state, so as in here, if we have to start from the maximally mixed state, then we can say that we got a Kusuoka measure associated to this family of operators. Okay.
Sorry, one simple remark. Here we assume that U unitary matrix operator is the same every time, but
yes,
would you get also probability vector and another Kusuoka measure if you assume that those U's can be chosen also from a set of U's, like this U after the second step is different U2 that U1 after the first step? So basically, ask if you would have in the center one U like U1. Moment, just a second.
Oh, okay, we can like,
Yes.
not entirely sure, but I think we can like here, we can define like subfamilies of those operators. Like, yes. I don't know, something like that with UA.
So I was thinking here to put like one number and let's say put here U2, okay, and put here, let's say, to have different U's.
Like so you mean a different U in each AI,
yeah,
or?
For instance, no, a different U in each time step.
As long as it's a finite family of U's, I think that would work, because we could like consider an extended family of operators.
Different unitaries, and you choose, maybe not randomly, but let's say between time 0 to 1, you have U1, and from 1 to 2, you have U2, and so on. So it would be a more general strategy.
Yes, I think that would work. Yes.
Thank you.
Okay, so also I'm very much prefer this trace formula, but in many papers you can rather find this squared norms of a product of matrices as the definition of a Kusuoka measure. So I've given it here. This obviously arises from the fact that this this row disappears in here. So in fact, we've got exactly the squared norm of the product of matrices which are inside this trace, right? But actually, I will rather stick to the trace formula. But this sometimes happens that a paper starts with a sentence that a Kusuoka measure is defined as the squared norm of a product of matrices. So this is where this squared norm actually arises. Okay, so now I would have to get back a little bit because I rushed in here. Get back to the slide with the definition of Kusuoka measures, because we now have our Kusuoka measure produced by our quantum system, and there's one more result proved by Kusuoka himself, and this has to do with the ergodicity of those measures. And Kusuoka's theorem says that if the family of operators we're dealing with, the family of operators which actually defines the measure in question, is irreducible, then the measure is ergodic. And irreducible here means that there does not exist a non-trivial subspace of CD which is invariant under each of these operators. So this is kind of geometric condition which from some point of view looks nice, but from some other point of view is not nice, because it's actually hard to quickly verify if there does not exist such a subspace. And it's also in particular, it's like hard to write a code that would check that for a given family of operators. So actually what I was interested in was to like study this irreducibility condition and maybe try to find some better way to express this condition. But the original Kusuoka result is that a family of operators is reducible, then the associated Kusuoka measure is ergodic. There's also one more result along those lines, which also says that the measure is ergodic, but the condition is that there is exactly one initial state satisfying this condition, let's say star. But again, this is not that simple to verify if there is only one, because we showed that the maximal mixed state is okay, but it's not obvious if there are other states like that. And it's also not obvious if there is an invariant subspace or no. So it's like worth looking at to see if we can come up with some better condition for ergodicity. Right, so let's move on. And actually, what I've got is while trying to find a better way to express irreducibility, I actually find out that Kusuoka's condition can be in fact reversed. So this irreducibility of operators is not only sufficient for ergodicity, but it's actually necessary for ergodicity. But I only did it for two specific types of measurements. It's mainly projective measurements that consist of two projections with ranks 1 and d-1. Also for rank 1 POVMs, but as someone has already observed, in the case of rank 1 POVMs, we've got a Markov measure And for Markov measures like ergodicity, we know when the measure is ergodic, there's like nice characterization via irreducible transition matrices, right? So this was not that exciting. What was more interesting was this case of projective measurements with ranks 1 and d-1, because here our sequences of outcomes are going to be definitely not Markovian.
I'm sorry, Anna, could you please remind us what it means that a measure is Markovian and what are the consequences of such a statement?
Like where? Like here, I only mean the sequences of outcomes are not Markovian. And the Markov measure was, it was on the first slide, it was the measure where the string I1, I2 up to IN, the probability of such a cylinder set was the probability of the initial symbol and then the probabilities of transitions.
So in a sense, it factorizes, it does not depend on the earlier moment in time. Okay,
exactly.
Thanks. Yes, I hope this is understandable. And what about the word ergodic? What is the simple interpretation for non-mathematicians?
Like ergodic measures are the simplest shift invariant measures in our case. Like those are the external points of the set of invariant measures.
Yes, but perhaps there's a simpler intuition behind it.
You mean the invariant set? The only invariant sets are trivial, right? So the whole space or
yes.
Or
okay. So in my understanding, the simplest way is to say that the average of a phase space is equal to the asymptotically to the average of a time of a trajectory. Somehow to have some physical interpretation. Is this correct?
It is. Yes, it is. We would need because in order to compute those averages, we would need some function that would return us numbers. So I didn't think about it immediately, but yes, exactly.
So in some sense, okay, it's not equivalent to a chaoticity in the system, but somehow you could have a chaotic measures which are ergodic, but also ergodic which represent system which is not chaotic. Yes, Wojtek?
Is weaker. The ergodic measure is the measure for which the ergodic theorem holds. So it's exactly what you said.
So,
but it is weaker than chaoticity.
Okay, so if you have a chaotic system, then the invariant measure is definitely ergodic, has to be ergodic, yes?
Yes.
Okay. Thank you for this reminder. Okay, good so.
Okay, so the rest of the talk, I think, will be devoted to this first type of measurement for which this Kusuoka's condition can be reversed. As I said, because for rank 1 POVMs, it's not that exciting because it's like studying once again Markov measures is not that exciting. So we'll focus rather on this first family of measurements. And an example of such a measurement, along with some example of measure which it produces, is in here. We fix a unit vector z. It will like define us a measurement which will which splits our space into like this rank 1 projector P0 and the rest, right? So this is d-1. This is the rest of the space. And so what are post measurement states f0 of something and f1 of something will specify. If we get the result 0, it means the post measurement state is this point, right? Because like getting 0 means we're measuring with pi0 and it's rank 1, so there's no space for the state to be anywhere else. But if the measurement result is 1, then we've got the whole d-1 dimensional block body at our disposal. So in here we've got actually CIF3. So here we've got the block body of a two-dimensional system. So the block ball. So here we've got the example for dimension 3. But on the left-hand side, we're gonna have like computations for general D. So what now happens if we start from the maximally mixed state? In the first measurement, we choose our subsystem to which we go with probabilities proportional to dimensions of our probability. So here we've got 1/3. Here we've got 2/3. And the post-measurement states at which we arrive from the maximally mixed states are the locally maximally mixed state of our subsystem. So here there's, like, as I said, there's only one state in the subsystem, but in here we've got the locally maximally mixed state of our block ball, so the center of the block ball. So this is the very first measurement, and now we're gonna like see some very specific situation. Namely, we have to take into account now the unitary evolution U, which will like evolve the whole system. And the very specific case which I want to consider is when this initial vector Z, which defines the measurement, is actually an eigenvector of U, which means that actually our two subsystems are U invariant, because here we've got one eigenvector of U, in fact, and so all the remaining two eigenvectors of U sit in the block ball, right? Which means that the block ball is invariant under this dynamics, and which means that the invariant dynamics of the ball means that the ball is rotating. We've got some local unitary dynamics on the ball. And so we are sitting on the very center of the ball, and the ball is rotating. So it's not very exciting for this state, because all the time it sits at the same place, right? The ball's rotating, but we are in the very center. So not much happens for this state, which means that if in the very first measurement we've got the result 1, we're gonna have the result 1 for the rest of in all the other measurement. So with probability 2/3, we've got the sequence of 1s, or if in the very first measurement we got the result 0 and went to this projector P0, we're gonna have the same result 0 throughout the rest of the experiment. So this system is not very exciting, as you can see, and also in the general case of dimension D, the result is as I've just explained. So with probability 1/D, we've got the sequence of zeros, and with the complementary probability, we've got the sequence of 1. Those are like Dirac deltas in here. So this resulting measure is definitely not ergodic, because I could write it as a convex composition of some other shift invariant measures. And we can also see how it agrees with the reducibility condition, right? Because if we now take a look at those two operators, we can see that the space spanned by the vector Z is actually invariant under both of them, because P0 U dagger, I can like skip the square root, because those are projectors. So this under 0, this acts on Z as pi0 I can ignore, and this is the eigenvector, so this is some eigenvalue times z again. And as for the other operator, this is z, and this is a projection on the subspace orthogonal to z, right? So this is actually your dagger on the zero vector, which is 0. And definitely 0 belongs again. So we see that in this very simple example that actually ergodicity and this invariance, this reducibility, so the existence of an invariant subspace actually have something in common. And also this has something to do with the eigenvectors of u being involved in the measurement, right? Or in other words, with the measurement respecting the eigenspaces of u. And actually what happens is that I told you that I managed to reverse this Kusuoka's condition. So Kusuoka's theorem was that irreducibility implies ergodicity, and I managed to reverse that. But actually what I did was I found another equivalent condition, which is like much more user-friendly than the irreducibility of some family of operators. Namely, it says that the ergodicity of the Kusuoka measure and the irreducibility of the family of operators is equivalent to the fact that no eigenvector of u is orthogonal to z. And in our previous example, actually, we had as many as 2 or d-1 in general eigenvectors of u which were orthogonal to z, so it produced non-ergodic measures. So equivalently, we can of course say that the non-ergodicity of u is equivalent to some eigenvector of u being orthogonal to z, which can be quickly and easily verified with a software, I think, which makes this condition much more friendly than the reducibility. And of course, the corollary of this theorem is that if u and pi are chosen at random from some reasonable distributions, then generically our Kusuoka measure is gonna be ergodic, right? Because again, this has to do with checking if some eigenvectors of u are orthogonal to z, and if there's some generic u which has like no, in which there are no, in which all the eigenvalues are different, right? So there are no degenerations in u, and then if you choose the measurement pi of this form at random, so in fact you choose like one direction of to project on, and the rest of the space is the other part of the measurement, then the probability that you will by accident cover some eigenvector of u is like 0. So generically, the Kusuoka measures are gonna be ergodic. And also, like the proof of this theorem is not very much complicated, but a bit technical. Here, this is like pure linear algebra, and in here actually we use the definition of ergodicity. By the definition of ergodicity, I mean the condition that if some subspace of sequences is shift invariant under this measure, then this has to be trivial. So it has to have measure either 1 or 0. But what was like most useful in the proof of this theorem was an equivalent expression of the irreducibility, in fact, because if pi is a POVM consisting of scale projections, so either a rank 1 POVM is okay here, or this pi which we consider here is also okay. Then you can disentangle the irreducibility. Yeah, we don't have to consider the composed maps as in here, but we can like check the invariance of a subspace under U and separately under the projectors. So if you are bound to take a subspace which is invariant under U, then we know what subspaces are invariant under U. Yeah, so those are the subspaces that are spanned by the eigenvectors of U. And then we only have to check if the projectors that make up the measurement agree with the eigenvectors of U. So the geometric interplay between the projectors that make up your measurement and the eigenvectors of U, or eigenspaces of U. So this is nice. This like simplifies a lot the reasoning, and also it's much better for like imagining the thing, because like checking invariance under the composition is highly intuitive because of this additional rotation applied after you check the projector, and in here we can like disentangle it. Right. So this is my main message, that ergodicity is in fact invariant, is equivalent to the eigenvectors of U not being orthogonal. The setup in here, then your Kusuoka measure is gonna be ergodic. Questions?
Well, perhaps there will be a few, but do you allow now for questions to the entire talk or only to this statement?
I've got the summary slide.
Okay, so I will wait.
Highly unusual for me, so let's maybe go through the summary.
Yes,
and
yes.
Then we will have questions to the whole of the talk.
Please do.
So yes, the repeatedly measured systems produce Kusuoka measures, provided that we start from the right state, and the maximally mixed state is definitely the right state. But I don't insist that it's the only right state, but it's the simplest state which we can verify that it is all right. But they can be other initial states which will lead to Kusuoka measures. And Kusuoka's sufficient condition for ergodicity. So I mean here this irreducibility of the family of operators that make up the quantum channel that describes the evolution of our system. This sufficient condition is also necessary for two types of measurements. And in these two cases, quantum systems that generate ergodic Kusuoka measures can be neatly characterized. By neatly, I mean here in the case we discussed of 1 plus d minus 1 projective measurement. It was this eigenvectors of U cannot be orthogonal to Z. And also for rank 1 POVMs, there's a nice condition which geometrically describes how the vectors which build up the measurement has to obey the eigenspaces of the unitary evolution. And also there's a bonus result, which I didn't focus on yet, but actually a byproduct of all this theory is that Kusuoka measures generated by those 1 plus d minus 1 POVMs are time reversible, in the sense that the probability of getting some string of outcomes is exactly the same as the probability of getting the string of outcomes, but in the reverse order. And this is like not very difficult to check. I would even say it's like an elementary proof. but it's like highly interesting because the distinguishability between those two probability distributions of like forward and backward are sometimes used to quantify entropy production of, or even to quantify the arrow of time, which is like given by our system. And in here, actually, you cannot say in which direction time flies if you only look at the outcomes produced by such systems. But this has, in principle, this has nothing to do with irreducibility. This is like via direct examination of the probabilities of string of outcomes. But still, I think it's kind of interesting.
Yes, so thank you very much, and especially thank you for finishing perfectly in time. We can now start the discussion. Who would like to pose a question? Please. So to give you more chance to think about question, I will now ask concerning your first remark. You said that if you start with maximally mixed state, then you definitely produce those Kusuoka measures. And how do you think? What other states are good as well to produce such a measure?
For instance, pure states that that arise from the eigenvectors of U.
Okay.
I mean,
let
me get back to
those states convex. If you now take the mixing of maximally mixed state and this pure state, such a, let's say, interval at the Bloch sphere inside, it will also produce such states?
In here, yes, because actually the condition is that the I row dagger. This is like the quantum channel we're considering, right? And the initial state is okay if it's invariant under this channel, if it's a fixed point of this channel. So in here, yes, you're right. But there may be like cases when the dynamics on the Bloch ball is like less trivial than in here. And it may happen that the maximally mixed state is okay. There is one pure state at the boundary, which is also okay, but the states in here are not okay.
Okay, I see. Good. Thank you very much. So are there further questions?
Two questions in the chat.
Yes. Thanks for this advice. So maybe I will read them. Yes, Oliver. Oliver had a question. I think his microphone is not working, so I will read it for him. First, are there any known cases where Kusuoka sufficient condition is not necessary? This is the first question. Kusuoka sufficient condition is not necessary. Yes, Anna, can you hear me?
Can't. Yes, I'm thinking, but I can't think of directly of some example.
Okay, and the second question was, do you know anything about the infinite dimensional case? I guess this is very different since there is no maximally mixed state. Good point of Oliver. Yes.
I wasn't considering like the infinite dimensional case. No. As for the first one, I would start looking into measurements where the measurement operators are actually not scale projectors. Then I think so. Some for projective measurements, actually, I'm not even sure if 2+ d minus 2, how it would behave. But in principle, I would start from POVMs on small dimensional spaces, but POVMs that don't consist of scale projectors.
Okay, thanks. Are there further questions? If not, let me ask another one. So have you considered, let's say you have a probability vector which grows in time, the length of the vector. Have you considered entropy of such a vector and how it changes with time? So of course it's related to the notion of dynamical entropy. So it has the physical meaning of the time derivative of entropy with respect to time.
Don't quite get the answer. What's the probability vector that grows in time?
Well, the vector P, Kusuoka measure, depends on index I1, I2 up till In. So the length of the vector, the length of the series depends on time, yes? But in principle, you can consider entropy of such a vector and look for the average entropy and then how it changes with time, this entropy. Okay, but it looks like you were not studying this. Or Wojciech, you have any comments?
Karol, do you mean dynamical entropy of?
Yes, something like this. So basically, first, for those who are not aware of dynamical entropy, I just ask a question. Can we say anything about the entropy of such a vector, probability vector, and how this entropy changes in time?
But maybe it is not clear what you mean by entropy of the vector, because for dynamical entropy, the answer is yes, and Ania computed this quantity, but it is not the same as the entropy of the vector. I mean, it was.
Wow. It is related to if you compare how this entropy changes in time, yes?
You mean logarithm of this probability, yes, over something, over n.
Okay, so in short, I was asking whether you'd consider the entropy of basically entropy of such a vector.
Entropy of the whole system.
Yes.
Because there is a theorem that logarithm of the probability over n tends to the dynamical entropy. That's Shannon-Macmillan theorem. So in this sense, I think the answer is yes, because Ania computed the entropy, in this case, 1 plus 2. So Ania?
Because don't get the idea of the.
Maybe the term entropy of the vector is not clear.
Entropy of a probability vector, like sum over I, pi log pi.
Yeah. So that's the
probability vector. You
okay.
Entropy.
That's the entropy of the system.
And change it. Look how it changes with time, with small n.
So in this case, the answer is, I think, yes, for 1 plus 2 system, for PVMs. So, but yes.
Good. Thanks a lot. So let me ask the last time, are there any further questions?